Okay, everybody, I'm going to walk you through question number 4 from the lesson 9 AGP problems, just because I went through your assignments and it looks like a lot of people are having trouble with it. So there's a few things that you need to know about for this assignment, or for this problem. The first is a polymerase chain reaction, or PCR. This is something that you should be familiar with from your other classes, but we'll go through it briefly here. The other thing that you need to know about are the differences between nucleotides and what their structures are. Okay, so let's get started with what is going on in this problem. So here's our DNA sequence that we were given with the 5' to 3' ends. So we know the phosphate's on the 5' end. And just to show you, I've drawn the complementary strand of DNA as well down here at the bottom. And that is going in the opposite direction, 5' to 3'. So this is the DNA molecule that we're given. Okay, so at the very beginning of this problem, it talks about the ingredients that they're going to add in. And the first step is going to be that you're going to heat that up so that the DNA strands will separate from each other. And that's what we call denaturing. Okay, so instead of these forming bonds like they were back here with each other, they're going to separate into two different strands. Okay, so the next step will be annealing, where a primer, which they gave us, will bind to the complementary DNA strand. Okay, so this is the primer that we were given. And so my question to you is, where will it bind to this template DNA? So we're going to call this blue strand that they gave us the template DNA, and then the green strand with the primer will be our newly synthesized DNA strand. So the first step that's critical is figuring out where this primer is going to bind to the template DNA. So if you think about it, this is also going to have a 5' and a 3' end, right? So if you think about just directionality, you'll know that if it binds to this top one, it's going to have to bind in the 5' to 3' direction, since this one's already running 5 to 3. This one will have to run in this direction, 5 to 3. Okay, if it binds to the bottom strand, it'll be able to keep its directionality, so 5' to 3', and it will have to find its complement in this bottom strand, and it'll run in the direction it's already going. I'll just tell you right now that these primers always bind in the reverse orientation to the 3' end of the strand that you're given. Okay, so I'll show you this. So we started out with it running in this direction with the T on the 5' end. And so we're going to reverse that. So you have the T on the 5' end, but it's running in the same direction. It's just the reverse orientation. Okay, and then hopefully you can see that that lines up and complements this top strand, the end of it. So you have TA, GC, GC, TA, TA. So it'll match that sequence from the original strand you were given. Okay, so it's always going to bind in that direction. We're not going to worry about this second strand anymore. It's not important to our problem. Okay, so we're just going to get rid of it. Okay, so then for the extension part of the PCR, these bases are added onto the primer so that the rest of the template DNA can be copied, and that's through DNA polymerase 3, as you should know by now. Okay, so all of these bases will be incorporated into that new strand, and you'll get a copy of your original template DNA strand. Okay, so that's the basics of PCR. So you have the denaturing, where the strands separate. You have the annealing, where the primer that you've added into it will bind to your original template, and we know now that that always happens in the reverse orientation for the primer on the 3' end of the template DNA. Okay, and then we have extension, where these bases are added so that the template DNA can be copied. Okay, and that's done by DNA Pol 3. Okay, so in question 4a, you're told that you're adding different nucleotides to this reaction. Okay, so the template DNA is always going to be the same, the primer is always going to be the same, and the enzyme will always be the same. The only thing that's changing in this reaction are the nucleotides that you're adding. And so in Okay, so in 4A, you are given the A, G, C, and T, and these are the deoxy ribose nucleic acids. So what does that actually mean? So let's take a look at the structure of what we're talking about. So the D refers to that it's a deoxy, so this is deoxyadenosine triphosphate, so the DATP is the example that we're looking at here. So this means that the sugar that we have is a deoxy sugar, so this is what's in DNA instead of RNA, and you can tell right here that there's no hydroxyl group, so this is the deoxy form of it. So that can be variable, so if this is a ribose sugar, you're going to have the OH on there, okay? And you will no longer have the small d at the beginning of this, indicating that it's a ribose, okay? The other thing that can be changed are the number of phosphates that are on here. So you can see there's 1, 2, 3 phosphate groups, which is denoted by the T, that it's a triphosphate. That can also be a monophosphate, which is denoted with an M. The other thing that can change is the actual base. So this is adenine. It can also be the other 3 or 4. Okay, and this is stuff that you should have learned in lesson 8, if not in previous classes. Okay, so let's just take a look at the difference between deoxyadenosine triphosphate and just the adenosine triphosphate. So that, like I was saying before, that sugar would have the hydroxyl group there. Okay, so this would indicate that it would be used for an RNA molecule rather than a DNA molecule. Okay, so going back to our problem, in 4A, you're given all of the bases that you need. So basically, what's going to happen is these are just going to attach onto your primer, and with DNA polymerase 3, they're going to go ahead and be incorporated into that new DNA strand. Okay, you're going to get all the way through. All of the nucleotides are the appropriate ones that you need, so you're going to build that complementary strand. Okay, so in 4B, oh, and I should say that the question asks that you do not give the sequence of the primer in your answer, okay? So the primer ends with these 2 G's, so we would just cross that out, and this would be your answer for that. Okay, so in 4B, you're given the nucleotides. They all look very similar to in part A, except for you're given CMP instead of CTP. So going back to our structures, what does that mean? That's a monophosphate instead of a triphosphate, okay? And that cannot be utilized by DNA polymerase 3, okay? So as soon as you get to a sequence where you're going to need a C incorporated into there, you're no longer going to have that as an option, okay? That's not going to work and the reaction will stop. Okay, so what would that look like? So the end of our primer, we said, are these double G's. So the next one that would be incorporated is complementary to the T's, so that would be an A. And then you have a G coming next, so you would want a C to be included right here, and you would continue to build off of that, right? Well, we already said that's a monophosphate. We cannot use it, okay? So the only reaction that would be allowed to occur here would be adding the A onto your primer. And since we're not supposed to include the primers in our answers, we're going to cross that out, right? The only thing that you would have would be this A. Okay? And then in 4C, you're given 1, 2, 3 regular nucleotides that we would generally use for this reaction, and then a UTP. So the U should occur to you that that's only found in RNA, so we can't use it, right? So the same thing is going to happen that happened in part B, where you're going to want to start incorporating these bases to build onto this primer in this direction. So you would get an A incorporated in there, and then you would get a C in. The C's are now fine. You have DCTP, so that's fine. And then you would want to do a T to match this A, right? Well, you don't have any T's. Instead, you have the U, and that's not going to be okay. All right, so that'll halt the reaction as well. Okay, so you'll get an A and C added on this time, but as soon as you try to get the T in there, the reaction's going to stop, okay? So we'll cross off our primer, get rid of that, and our answer will just be A and C. Okay, and then moving on to for D, the nucleotides that you're adding are, you have a regular A, a regular C, a regular T, but instead you're given GTP. So this means that it's not deoxy, right? So this is a ribose sugar instead of a deoxyribose. So this would also be used for like an RNA molecule. Okay, so once again, we're not going to be able to use that. So once you're starting your reaction, once you need a G to be incorporated, the reaction's going to stop. Okay, so we'll go ahead and take a look at what that looks like. You'll get the A in there, you'll get the C in there to match with the T, or with the G, you'll get a T in there to match with the A, and then you run into this C, and you're going to need the G, the complementary base, right? Well, since this is a GTP, that's not going to be able to be incorporated. The DNA polymerase 3 will stall and fall off, and that's the end of your sequence, okay? So once we take out the primer, again, the answer that we're left with is ACT, okay? I hope that that has helped and made some sense. Please email me if you have any more questions. Thanks, guys. Good luck on your test.